دي. تفضلوا يا 20 minutes ان شاء الله وبعد كده discussion 10 minutes.
Hello everyone, I'm Lujine and my topic is depression detection in speech using generative models. These are the things that we will tackle today. Let's start by the introduction. Do you know who these people are? This is Serena Williams and this is Michael Phillips, and they're both pro players, but they suffered from something else, which is the depression. Did you know that almost 280 million people around the world also suffered from depression? Some remain undiagnosed and others avoid getting treated. This is because traditional depression detection is extremely time-consuming, as it takes at least 2 weeks for a therapist to diagnose someone with depression. Another reason is that many people avoid seeking help because of the stigma around the mental health treatment and how society judges people, making traditional depression detection not always accessible and leaving more people untreated and risking their lives. Moreover, to this day, because of medical data privacy, depression-related data sets remain scarce. Lastly, athletes' mental health is being overlooked. As a developer, having limited availability of depression-related speech affects model training, which makes it a bit challenging to achieve high model accuracy. And also, it's a bit difficult to generate high-quality synthetic speech and accurately evaluate it. These are some of the papers that I've read, and they all use the same data set, which is the DICOS data set, and also they have the common limitations, which is the small data set size, but more importantly, the data imbalance. So my main objective would be utilizing generative models to generate more depressed speech data to address this class imbalance part. Then developing a machine learning algorithm for depression detection in speech. Thirdly, analyzing the impact of different feature extraction techniques. And lastly, evaluating the generated synthetic speech and the results of my model. So, what if your voice could reveal more than just words, and by using AI, we could save more lives? Let's find out in my methodology. A quick overview is that I want to detect depression in speech by analyzing the acoustic features, which is the tone, the pitch, the jitter, meaning how does the speech sound, rather than what's actually being said. Then I want to use this generated synthetic speech to address the data scarcity part, and to try and balance the data sets, and to see the effectiveness of the synthetic speech on the model's performance. Let's start by the synthetic speech generation. I've taken all of the transcriptions of the EDAG dataset, and I'll be telling you more about this dataset later. Then I've done few-shot prompting in order to paraphrase these transcriptions. This was the input to the Gemini 2.0 Flash model, and then it gave me as an output the newly generated paraphrase transcriptions. Now I've got the text, but I'm working on speech. So I used another model, which is called Koki text-to-speech model, in order to generate this speech. So this is now my main output. This is an example of the paraphrase transcriptions, and I paraphrased them because I wanted to retain the meaning of the audio files in the same dataset in order to be able to use the same labels provided. Let me show you a quick sample of the generated speech.
Feel that way. More like numb. Just trying to keep moving and stay healthy, I guess. Lately, nothing seems to bring me joy. Being active and healthy outdoors feels impossible. Activities like hiking, biking, rollerblading, and skateboarding used to bring me joy. But now they just feel empty.
Moving on to the overall project plan. As you can see, there are two main inputs. The first one, which is the generated speech, which I was telling you about, it's here as an input because I want to see if it could boost my model's performance. The second input, which is the main audio data, which is my data set. I requested this data set from University of Southern California. It's called the eDICE data set because it's the extended version of the DICOS data set, which was used by other papers in the literature review. It consists of 274 audio files, and as you can see, there's a huge data imbalance because less than 25% of the dataset are depressed files. Then after augmenting my dataset, now I have a total of 338 audio files, making 130 depressed audio files, which is almost 40% of my dataset now, which is better than the previous imbalance. Moving on to the pre-processing stage, which I removed the silent parts and the things that would distract my model, like the interviewer's voice. Let me show you a sample of how now the audio sounds. This is the real sample. Moving on to the feature extraction part. I did 2 experiments. So for experiment 1, a part of the feature extraction, which is the segmentation, I've taken all of the depressed participants and I've done 4-second segmentation, and for the non-depressed participants, I've done a 12-second segmentation. This is because the number of non-depressed participants is almost triple the number of depressed participants. So this is an attempt to create class balance and generate more training samples of the depressed audio files. Then for the feature extraction, this is a frequency-based feature extraction where I've extracted 15 features for each segment. 13 of them are the MFCC coefficients, which are the spectral features for the audio file, which captures vocal characteristics important for identifying depression. Then 1-0 crossing rate, which is the temporal features, which assesses the changes from positive to negative and how the signal changes. Then the spectral centroid, which is the center of mass of my audio file, meaning how dull or how bright the audio file is. And for a depressed person, as he tends to have more of a monotonic voice, he would have less of these sign changes in the 0 crossing rate and more of a dull spectral centroid, because he would have less high frequencies. Then I used the same split provided in the eDiag dataset, which is 60% training, 20% testing, and 20% for development. Moving on to the second experiment, but let me tell you first about the Wave2Vec 2.0 model. It's a deep learning model used for automatic speech recognition and audio feature extraction. It was developed by Meta AI, and in my second experiment, I used the base version of it. So firstly, for the segmentation, I've done a 10-second segmentation for all participants, but this was not because I wanted to create a class balance again. This was primarily used for memory management, because it was not memory efficient to load the whole audio file at one time when I was doing my experiment. Then, for the feature extraction, I used Wave2Vec for each experiment, for each segment, and it computed statistical features. Then it returned for each audio file a 4-dimensional feature vector containing mean of all means, maximum of all maximums, mean of all standard deviations, and lastly, minimum of all minimums. Then the split that I used in this second experiment was from the scikit learn train test split library. Then I took 20% for a testing set, then the remaining 80% I divided them into 10% development set, and the remaining 70% were my training set. Moving on to the last stage, which is the machine learning model, which is the last one before finally getting the final depression label, which is the main output. Let me tell you why I used machine learning instead of deep learning. It's because deep learning models require huge amounts of data to be trained and produce good results. However, this wasn't the case in my project because of the small data set size and the huge data imbalance that I had. So traditional machine learning models posed a better solution, as they could perform well with smaller data sets, and also they've got lower computational costs, which is more suitable because of the GPU limitations that I had. For experiment 1, I've used 3 classifiers, which is the support vector machine, random forest, and logistic regression. Then I've done hyperparameter tuning for all of these classifiers in order to achieve the best results. Then each model classified each segment individually And then, in order to know the final participant label, I've done majority voting for all of the segments for each participant. Then for experiment 2, I used the same 3 models. However, I've added another model, which is the XG Boost model. This is because I wanted to experiment more and to see if I could achieve even better results with another model. Then I've computed class weights in order to address the data imbalance part, and each model gets its own optimal threshold depending on the development set. Lastly, models make participant level classification right away because I'm not using any segments here. Then for the evaluation metrics, I use the standard evaluation metrics for the machine learning, which is accuracy, precision, recall, and F1 score. Then for synthetic speech evaluation, I use the Fréchet audio distance. It's a quantitative metric used to evaluate the quality of the generated speech by comparing it against real audio files. So I've taken all of the depressed audio files in my eval dataset and all of the generated depressed audio files, and then I used Google's Biggish model in order to extract embeddings for all of the audio files. Then I calculated mean and covariance and substituted in this equation to get my final score. Then I wanted something to back up the FAT score even more because it's not widely used. So I used human-in-the-loop evaluation, which is a qualitative metric. It's using humans' feedback to measure the quality of the generated synthetic speech samples. I did this using Google Forms questionnaire, where people listen to random audio samples of both real and synthetic speech, and then they answered 4 questions. 3 of them are rating on a scale from 1 to 5, the naturalness, the clarity, and the emotions of the audio sample that they've just heard. And lastly, it's asking the respondent whether they could evaluate the audio file as synthetic or real. Let's take a look at my results. For experiment 1, I've conducted 2 versions. Version 1, where I trained and tested my model using real data only, and version 2, I've trained my model using the real and synthetic audio files, and then tested it using the real audio only. I didn't use synthetic speech in evaluating my model because it's not realistic and it doesn't reflect the real-world applications. For experiment 1, as you can see, SVM has the best performance, and for version 2, it also has the best performance, which also shows the improvement in its scores, highlighting that synthetic speech really did improve the metrics. For the second experiment, I've done the same 2 versions, where version 1, I trained and tested my model using real data only, and for version 2, I trained my model using real plus synthetic speech, and then tested my model using real data only. As you can see, for version 1, SVM had the highest performance. However, it wasn't consistent, and its metrics have actually decreased in the second version. However, the XG Boost model had the best overall performance, in my opinion, because it remained consistent and it showed a slight improvement in the second version. For the results of the synthetic speech, the FAT score, when it's lower, closer to 0, it means that the generated speech has a better quality, which is closer to the real audio. In this experiment, I had a FAT score of 9.26, which means that the generated speech has good quality. However, there were some differences from the real audio. For the human-in-the-loop evaluation, this is the first question of a synthetic speech sample, asking how natural this audio file is. As you can see, almost all of the scale has the same number of responses, except for number 4, which is leaning more towards the not natural part. So this backs up my FAT score, meaning that some people were confused. However, there were some that were able to identify these differences. This is asking about the clarity, and as you can see, almost 70% is rating very clear. Then for asking about the emotions in this audio file, as we can see, this graph is almost symmetrical. However, if we look closely, this is almost 70% of the data for the scale from 1 to 3, leaning more towards the strong emotions. Then for the last question, I wanted to compare a real speech sample result and a synthetic speech sample. This is because I wanted to show you that people were able to correctly identify both samples by the same rate, which is 70%. So, which is also very close to what my model's results were. This is the comparative results between experiment 1 and experiment 2. And in my opinion, I think experiment 1 had the better results than experiment 2, as it had slightly better high scores. To conclude, I think synthetic data has the potential to improve the results of the model. However, its effectiveness is highly dependent on the model type and the quality of the generated speech. And also, synthetic data presents a practical and a scalable solution for addressing the data scarcity part, especially in domains where privacy is a concern, like the medical domains. Lastly, depression could really be detected from the acoustic features only, providing a non-invasive approach for detecting depression. For the future work, let's start by the things I think needs to be done for the academic purposes. I think we need to experiment with multiple data sets and languages, because language won't be a barrier anymore, as we don't need to understand what's being said. We're only analyzing how the speech sounds. Secondly, we could improve the realism and generalization of the generated synthetic speech. This could be done by using more than one text-to-speech model in order to generate more synthetic speech. Thirdly, I think we could experiment with more deep learning models like CNNs and RNNs, because they're more sensitive to the audio features and the changes in them. And also exploring different techniques for handling the data imbalance. Lastly, this framework could be applied to real-world applications, like mental health monitoring for athletes, early school intervention tools to be used by counselors, and lastly, chatbots that identify depressive tendencies, which could be used by individuals or even as an assistant for a therapist. So this is my vision for people to be able to talk to an AI tool, and for this tool to be able to identify the depressive tendencies in the people's voice, and maybe give them a warning and an encouragement to go seek help. So what's my goal? It's faster, easier, and a more accessible depression for everyone. This brings us to the end of my presentation. These are my references. I would like to thank my doctor for his continuous support, and thank you all for attending.